Welcome. This is a lecture on abstract vector spaces. So let me remind you what the notion of a vector space is. It's simply a set together with two operations on it, addition and scalar multiplication. So addition is vector addition, and this dot refers to scalar multiplication. And what that means is that the elements of this set are called vectors. And if you have two vectors v and w, you can add them and get a new vector, v plus w, and that will also be in v. And similarly, if you have a vector in v and a scalar, you can multiply the scalar times the vector and get a new vector in v. And there are a bunch of properties that these operations are required to satisfy, which I'm not going to go over, but they're things like v plus w is required to equal w plus v, and so on and so forth. So I encourage you to go back and review this definition. So I'm going to spend a little bit of time on the basic example, which is consider the functions of a single variable x whose second derivative is minus itself. So that is to say, the functions, when you take two derivatives, you get the same function back with a minus sign. And the key point here is that even if you don't know an example of any such function, you can't solve this thing. You have no idea what the function is. It's just immediate that if the second derivative of f is minus f and the second derivative of g is minus g, then if you add those two functions, the second derivative of f plus g is minus quantity f plus g. That's just follows from the properties of derivatives. And so this thing is a vector space. If you add this v and g you're thinking of as vectors, if you add two vectors which satisfy this property, their sum satisfies this property. And scalar multiplication works also. So this is a vector space, just for abstract reasons, whether or not you know anything about it. Now, in fact, we do know a lot about it. We know that every function which satisfies this is of the form a cosine x plus b sine x. And that's a basic property. You can go back to your calculus course to see why that's true. And you think of this as saying that every function is of the form av plus bw, where v is the vector, so to speak, x, and w is the vector sine x. Okay, here's another very important source of examples of vector spaces which aren't just Rn. Let's start with Rn and consider a subspace of Rn. So Rn is Rn, but take a subspace of it. So, for example, take the following subspace of R3, vectors x, y, z in R3, such that x plus y plus z is equal to 0. That is a subspace of R3. What does that mean, it's a subspace? Well, to say that it's a subspace is to say that if v and w are vectors in v, then v plus w is in v. That's the definition of a subspace. So, well, that's exactly the definition of a vector space, after all. So, to say that something is a subspace of Rn is to say that it's a vector space in its own right. And the picture, of course, is just that you have something like a plane sitting inside R3. And the point is, it kind of looks like R2, but it's not R2. It's just an abstract vector space. Okay. Now, what we're going to do is all of the concepts that we talked about in the setting of Rn are going to carry over essentially word for word to the setting of an abstract vector space. So go back through the book and see span, basis, linear, transformation, the null space, all of these concepts work exactly the same way in the setting of an abstract vector space. And we're going to go through some of these. So, for example, let's talk about a linear transformation. So we've already seen the concept of a linear transformation from Rn to Rm. It's a map from, the other way I'm doing, Rm to Rn. And it's supposed to be a map which satisfies T of V plus W is T of V plus T of W. And similarly, T of C times V is C T of V. Okay, we've seen that already. Well, just say the same words again. Linear transformation from one vector space to another is a map from V to W, which satisfies T of V plus W is T of V plus T of W, and T of CV is equal to CT of V. So all I've done is I've replaced Rm with V and Rn with W, and exactly the same words and definitions apply. Okay. Here's another example, the notion of a subspace. What's a subspace of Rn? It's a subset which I'll call W. It's a subset of Rn, and such that if V and W are in the subset, then V plus W is in the subset. Well, and also scalar multiplication. What about a subspace of a vector space V? It's exactly the same thing. Just replace Rn with V, and you say that V and W is in W implies V plus W is in W. So, okay. So I think it's helpful now to sort of give a dictionary between these two pictures, between a concrete vector space Rn and an abstract vector space V, and how you sort of pass back and forth between the two settings. So one of the things is when you're talking about Rn, you're talking about linear transformations. Well, we really talk about matrices most of the time. So you have a matrix which is a map from Rn to Rm. In the setting of vector spaces, that's a linear transformation from a vector space V to a vector space W. And what I'm going to be using over and over again is that in the setting of Rn, linear transformations are given by matrices. So, for example, the null space of a matrix, that's what? It's a subspace of the originating space Rn, the vectors in Rn, which get taken to 0 by this matrix. And in the setting of a vector space, it's essentially the same thing. The null space of a linear transformation is the vectors V, which get taken to 0 by the linear transformation. And again, it's a subspace of the originating space V. And we talked quite a bit about the column space. What's the column space of a matrix is the span of the columns. Well, we talked about this in the setting of Rn. That's the same thing as the image of the linear transformation. So that is to say, in the setting of vector spaces, the span of the columns, which is a subspace of the target space Rm, that's what we're going to call the image of a linear transformation. It's the set of vectors in the target space W which get hit by applying T to some vector V in V. And again, this is a subspace of the target space W. So it's essentially the same concepts on both sides, slightly different words. But so let me draw a picture now. So when you have an abstract vector space V and a map two vector spaces V and W and a linear transformation from one to the other, the null space of T, it's a subspace of V which goes to 0, and the image of t is the things that you hit. And just a little bit of terminology, the image is the same thing as the range. So I will use those two terms interchangeably. Image of t and range of t are exactly the same thing. Okay, so now let's go on to talk about linear dependence and independence, and span and basis in a vector space. So we have vector space V, and everything I say, again, not to belabor the point, but it's just exactly the same words as in Rn. So you have a vector space V. What does it mean to have a set of vectors be linearly dependent? V1 through Vn are linearly dependent if what? If you can write A1 V1 plus A2 V2 plus so on and so forth, AN Vn is equal to 0. If there's a linear dependence relation where not all of the AIs are 0, exactly like in Rn. And if they're not linearly dependent, of course, they're linearly independent. Sorry, misprint here. If they're not linearly dependent, they're linearly independent. Similarly, what does it mean to say that a bunch of vectors span the V? Well, that says that every vector in V can be written as a linear combination of the vectors V1 through Vn. So any vector V is of the form B1 V1 plus dot 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 Bn Vn for some Bi's. And of course we say that this set is a basis if it's both of the previous. It's both linearly independent and spans, just like in the case of Rn. And of course, one last concept which carries over is the notion of dimension. You say that the dimension of a vector space is the number of elements in a basis. Okay. All right, so after all of that blah, 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 it's time to do an example or two. So let's go back to our favorite example, the functions whose second derivative are minus themselves. So this is this vector space that I mentioned earlier. So let's see. One of the vectors in here is the function cosine x. That's an element of this set, so that's a vector. And similarly, the function sine x, I'll call that v2. These two vectors are linearly independent. Cosine x and sine x are not multiples of each other. So I'm not saying anything difficult here. It's just you have to get used to thinking of these functions as vectors. So these two vectors are clearly linearly independent. And instead of taking those, I could have taken v1 to be cosine plus sine and v2 to be cosine minus sine. Both of these functions are in the space, so these are two vectors in the space. And let's take v3 to be cosine. So now I have three functions in this space. I claim that these are linearly dependent. Well, so I'm claiming that you can find a linear dependence relation between these three vectors. Well, let's see. If I add v1 and v2, that's cosine plus sine, and then plus cosine minus sine, and the sines cancel, and you get 2 cosine x. And, well, cosine is v3, so that's 2v3. So I see that v1 plus v2 is equal to 2v3, or v1 plus v2 minus 2v3 is equal to 0. that's a linear dependence relation. These vectors are not. These vectors are linearly dependent. Okay, so let's go back to our original cosine x and sine x. I've already mentioned that these are linearly independent. They also span. Well, that's because I said earlier that, oh, I'm sorry, that's a misprint. The second derivative is minus f. If that holds, then f is of the form a cosine x plus b sine x. So that's exactly saying that this vector v, which is in this space, is a linear combination of v1 and v2. So that says that v1 and v2 are a basis of v. Let's try two different vectors. Let's go back to our cosine plus sine and cosine minus sine. These are also a basis. They're clearly linearly independent, and there are two of them, and they span. So let's see, do they really span? So can you really, suppose you take a function a cosine x plus b sine x, can you really write that as something times cosine x plus sine x plus something else times cosine x minus sine x? Let's see. So what do I have to put in these blanks to make this true? Well, let's see. What I'm going to put here is a plus b over 2, and here a minus b over 2. And I claim that with those numbers, you've recovered this function f of x. So let's see. Let's group terms accordingly. If you just look at the coefficient of cosine x, that's here's this cosine x here, which has a coefficient of a plus b over 2, and this cosine has an a minus b over 2. On the other hand, the sine x terms are a plus b over 2 and minus a minus b over 2. And so when you regroup terms that way, you see that a plus b over 2 plus a minus b over 2, you cancel the b's and you get a cosine x. And similarly, the coefficient of sine, when you look at these, the a's cancel and the b's add, and you get b sine of x. So indeed, this is a basis. So that was basically just an exercise to show you that everything that you're familiar with in Rn can be done in the setting of these function spaces. Okay, so let's do one last example. Let's take the following set. Let's take V to be the vectors in R4. This is a subspace of R4. And it's the subspace consisting of the vectors, the sum of the coordinates are 0. Now, if you let T be this matrix, T takes the column vector x1 through x4 to x1 plus dot 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 x4. So, if you don't mind my switching back and forth between columns and rows a little bit, you see that V is simply the null space of T. And we know that the null space of a linear transformation is a subspace. So this thing V is a subspace of R4, so it's a vector space in its own right. So let's think about that a little bit. What is it? What's its dimension? What's a basis? And so on. Well, let's see. How do you find basis? So remember, that's going back to the technique of free variables and pivots and so on of parametrizing solutions of a homogeneous equation. And in this case, this matrix is very simple. It's got a single pivot, which is the first guy. And then the other variables are free. So it has 3 free variables. So I guess it's 3-dimensional. And let's find a basis of it. Well, we know how to do that. You look at the equation x1 plus x2 plus x3 plus x4 is equal to 0, and x 2, 3, and 4 are the free variables, so you bring them to the other side and you just say x1 is equal to minus x2 minus x3 minus x4. And you can vary x2, x3, and x4, and then x1 is handed to you. So this is a three-dimensional. This has 3 parameters. And to pick a basis, you do the usual thing. You could take x1 as take the v1 to be the following vector. Take x2 to be 1, and x3 and x4 to be 0. And then you get the vector minus 1, 1, 0, 0. Or you could take v2 by taking x2 to be 0, x3 to be 1, and x4 to be 0. And then you get minus 1, 0, 1, 0. And finally, you can take x2 and x3 to be 0 and x4 to be 1, in which case you get v3, which is minus 1, 0, 0, 1. And these 3 vectors are obviously in V. They're obviously linearly independent, so this is a basis of V. And again, V is a vector space. It's not Rn, it's not R3, it's just a vector space. It is three-dimensional, but it's not literally just R3. And one of the important points here is that this basis that I chose isn't the only basis. It's not even necessarily the best basis or the obvious one to choose. Here's another one I could have chosen. I could have chosen W1 to be 1 minus 1, 0. Start in the same way as before, but then take W2 to be 0, 1, minus 1, 0, and take W3 to be 0, 0, 1, minus 1. That's a perfectly good basis also. And that's one of the points about vector spaces, is they don't have an obvious basis. You have to pick one. Okay, that's a good place to stop.